Hi there, welcome to your first online lesson. Today we're going to start chapter 3 and specifically we're going to go over exponential functions and their graphs. So you may remember we've gone over a lot of functions over the past semester. We've learned about algebraic functions in specific, such as ax squared plus bx plus c equals 0. A couple of other algebraic functions that we've dealt with are linear functions, such as y equals mx plus b. Or cubic functions where we've got y equals x to the third power. But we haven't really looked into exponential functions. So what is an exponential function? It is when the variable x is actually the exponent. So in our previous algebraic functions, if you take a look at my pen up here where it's at, we've had it where ax squared plus bx plus c equals 0. X is part of the equation and it has an exponent, and in this case, the exponent is 2. Now, with regards to exponential functions, x is your exponent. So we can see here in our equation, f of x equals a to the x power. X is actually the exponent of this equation, instead of it being part of the equation as in our algebraic functions. So when you have an exponential function, the easiest way to determine it is when you have x as the exponent. And specifically, all exponential functions will follow the rule where a does not equal 1 and x is any real number. And a is called the base of that function. Okay, so let's actually see what the graphs of these functions look like and how they differ from algebraic functions. So first we're going to look at the functions that we already are familiar with, or one of them anyway. And that's y equals x squared. You can see it in the kind of dark brown line. It's a parabola. It's a parabola that we're very familiar with, facing upward. That's our graph of y equals x squared. But if you see the black line there, that's the graph of y equals 2 to the x. So I just wanted to show you how those two are different. So now actually let's look at the different kind of shifts that the graph y equals 2 to the x, or an exponential function, can have. And they're very similar to the shifts that we learned previously earlier in this year. So the first shift is going to be a reflection in the y-axis. And the way that you can tell it's a reflection in the y-axis is because the exponent becomes negative. So we have the equation 2 to the negative x. That means it's reflecting about the y-axis. So this point right here is going to flip across the y-axis and is going to start here instead. So our graph would start at this point and would be coming down about like this and going through. So this is the graph of the equation y equals 2 to the negative x. Okay, so now let's take a look at a reflection in the x-axis. So in the x-axis, it's our base that becomes negative. So our base here becomes negative. So remember, in the y-axis, it was our exponent. In the x-axis, it's the base that's negative that makes it a reflection in the x-axis. So a reflection graph would look similar to something like this. Where it's reflected about the x-axis. So I know I'm going through these a little bit fast, so feel free to pause the video if you need to take the notes. Okay, so now let's look at a horizontal shift and a vertical shift. A horizontal shift is going to be denoted by a number being added to the exponent. So instead of 2 to the x, we're going to have 2 to the x plus 1. And remember, in horizontal shifts, they're actually kind of backwards from what you think. So since we're adding 1, and it's going to be a horizontal shift, that means that it's going to move to the left 1 unit. So if we were to take this point right here and shift it over 1 unit to the left, it actually becomes this point right here. So that's our horizontal shift. And likewise, if we took our point here where x equals 1 and shifted over 1 unit to x equals 0, that's going to give you that point right there. And same thing with 2 when we move it over 1 unit. So we can start seeing our shift of our graph is going to look something like this. And excuse the rough draft here. It's not the easiest thing to draw with this equipment here. But that's roughly what your horizontal shift would look like. Okay, so now let's take a look at the vertical shift. So vertical shift is going to be when you add or subtract a number to the entire equation. So we have 2 to the x and then plus 1. And it's doing just that. So it's going to be increasing it by 1. So if we have the point here, all of a sudden it's going to jump up to here. And here we've got our point, which is right at about 2, so that's going to jump up 1 unit. There we go. So our new graph is going to look something like this, roughly, because remember, these are all jumping up about a unit. So the graph rises up 1 unit because it's plus 1. Okay, so now that we've seen the graphs of exponential functions, we're going to learn a little bit more about the natural function e. Natural base e, which is referred to as Euler's number, is actually an irrational number. E is a number. E is very similar to pi. It's an irrational number. It's constant. It won't ever change. And it's referred to as 2.7, and it goes on and on and on with this decimal. So like I said, e is a constant. It will never change. It's always going to be this big long decimal. Or we can just shorten it up to 2.7 for right now. Similar to pi, how we shorten that to 3.14, but we know that that goes on and on forever. And it's irrational. So e is used a lot in the natural exponential function. And in fact, e is the base of a natural exponent function. So remember, we have e to the x is our exponential function. This means that our constant a, or our base a, is equal to e. So that's the function, natural exponential function, e to the x. This function, and e in general, is used a lot in the real world, especially in science and business. So let's take a look at some business applications and equations for e. So the first thing is we're going to see a lot of information pop up on the slide, and I'm actually going to go through it pretty quickly because it's going to be more helpful when I go through the actual examples on the next slide. But e is used a lot when calculating interest earned, or if you were to invest money over a period of time, how much is that going to grow? And it depends on the type of compounding that you do or how many times you calculate that interest. That depends on how much it's going to grow. If you calculate or compound that interest continuously, so that means it's constantly updating, you're going to use this equation, A equals PE to the RT, or PERT. And we're going to see how to use that on the next slide. If you're compounding it a set number of times, you'll see that we're going to use this equation, A equals P times the quantity 1 plus R divided by N raised to the NT. E is not a part of this. You will not find E in this equation. It's only when it's continuous that you're going to use E. So feel free to pause this video right now if you need to write down what each of these variables mean. So to write this part down right here, but we're going to go over it and how to use these equations in the next slide. Okay, so first, before we get started, I want to make sure that you actually know how to input exponential functions into your calculator. So let's take the first example. We've got 2.3 to the x. We need to figure out what is the value of this function when x equals 3 halves. Or we can simply say 1.5. So in order to put this into your calculator, you're going to want to type in 2.3 and use your caret button to raise it to x. And then we're going to put in 1.5. So that's how it should look on your calculator. You could also put this as 3 divided by 2, but make sure you put parentheses around it if you type it in that way. Regardless, you should get the answer 3.488. Make sure that you got that. If you didn't, try it again or ask questions tomorrow in class. Okay, so what happens if we have E as our base? So up here, 2.3 was our base. Now we have E. So if you don't know where E is on your calculator, take a look at the button that looks like this, capital L, capital N. This is your natural log button. Above it, you're going to see e to the x. So that's what we're going to want to use. So in order to get e to the x, you're going to type in, or you're going to press the second button, and then press ln, and on your screen, you're going to notice that e pops up with the parentheses already there. So in that case, now we just need to type in our exponent. We want e to the negative x. So that means we have to put in our negative sign, make sure it's the negative and not the minus, or else you'll get an error. So negative 3.2. When you type that into your calculator, you're going to get the answer 0.408. Okay, great. So now you know for sure how to use exponential functions and how to calculate them on your calculator. So let's go back to those functions or equations that we just saw on the previous slide. So we're going to use both of them. The first one is when we're going to use the compounding equation, and the second is when it's compounded continuously. And so for the first equation, because we have n equals 4 and not continuous, we know right away this is the equation that we're going to use. So now simply we just plug everything in. So you should have what everything represents written down from the previous slide. So A is what we're solving for, so that is the account balance. So we're going to pretend that we're investing $1,000, that's our P. We're investing it, and we are going to invest it at a rate of 4%. So we're going to use the equation 1 plus 4%, but we need to put 4 as a decimal, so that's going to become 4.04. And then we divide that by the number of times that we're compounding it, so that's our n. So we're dividing that by 4. And we raise it to the nt, so that's 4 times 10. So this is what your equation would look like on paper. So make sure when you type this into your calculator, you're doing everything that we did above in the previous examples. If you get this into your calculator correctly, you're going to get the answer 1,488.86. So that means after 10 years of $1,000 being compounded at the rate of 4%, 4 times over a period of 10 years, you're going to have $1,488.86 in that account. So you've actually made $488.86. Now let's see what happens when we compound it continuously. So we're doing the same thing here. We're just going to be using our continuous function, which is A equals PERT, P-E-R-T. So we got 1,000 times E, remember that's a constant, raised to our rate, which is 0.04, times our time, which is 10 years. Okay, so if you plug that into your calculator correctly, you're going to get $1,491.82. So you can definitely see that this one's going to yield a little bit better interest or outcome for you. But that's how you use these equations. So hopefully you've learned a lot in this lesson. That's it. We're done for the day. But please give me your feedback when I see you. Let me know if I need to add stuff or if I'm redundant. You know, this is the first time I've done this, so I'm learning along with you guys as far as the online learning class goes. But anyway, I hope you guys have a wonderful rest of your evening and look forward to seeing you in class. Take care. Bye-bye.